Ever look at a skyscraper and wonder how it doesn't just tip over? Or how a gymnast can find that perfect, unshakable balance? Well, the answer lies in this really cool spot where physics and calculus just click. Today, we're going to dive into the center of mass. We're going to take these abstract integrals you see in class and turn them into the real-world balance points that, kind of keep our world from falling apart.
I mean, think about it for a second. If you wanted to balance a book on your finger, you wouldn't just stick your finger on the corner, would you? Of course not. You'd kind of instinctively hunt for that one single perfect point right in the middle. That exact point is what we're going to pin down today using the power of calculus.
So, formally, this magic balance point is called the center of mass. It's the unique spot where, if you could somehow squish the entire object's mass down into one tiny speck, it would behave in exactly the same way. Now, for a simple uniform shape like a flat piece of cardboard, this is just its geometric center, will be called the centroid. But what about weird irregular shapes? Or objects where the weight isn't spread out evenly? Yeah, that's where calculus becomes our superhero. Okay, so to find this point for pretty much any shape you can imagine, we need a solid set of mathematical tools. We're going to be using multiple integrals, and they are absolutely perfect for this job because they let us add up countless infinitesimally tiny pieces of mass across an entire object to find its overall balance. First things first, we calculate the total mass. We do that by integrating the density, that's the Greek letter rho, over the entire volume. Simple enough. Then we find what are called moments. Now, the easiest way to think of a moment is like a measure of leverage. It basically tells us how much the object's mass wants to rotate around a specific plane. We find it by doing another integral, this time taking a weighted average of each tiny piece of mass times its distance from that plane. And here's the best part. Once we've done the hard work of finding the total mass and the moments for each plane, finding the actual coordinates of the center of mass, we call them x bar, y bar, and z bar, is just simple division. Seriously. Each coordinate is just its corresponding moment divided by the total mass. That's it. Okay, quick heads up, because this is a super common trip up. You have to notice how the moment about the YZ plane, MYZ, is what we use to find the x coordinate. It feels backwards, I know, but it actually makes perfect sense if you just pause and think about it. It's measuring the weighted distribution of mass away from the YZ plane, and that's exactly what the x coordinate does. All right, enough theory. Let's put these formulas into action and see how they work. We'll start with a classic, two-dimensional example, finding the centroid of a nice, simple triangle. We're going to follow a really straightforward three-step game plan. First, find the mass. Second, calculate the moments. And third, we just divide to get our final coordinates. Let's do this. So for this problem, we're going to assume a uniform density of 1. This is a really common simplification in these types of problems, and it just means that the mass is numerically the same as the area. For our triangle, the base is 1, the height is 2, so the area, and therefore the mass, is just 1. Easy. Next up, we calculate the moment about the y-axis, my. This double integral might look a little fancy, but all it's really doing is summing up each little sliver of area, which is dy dx, and multiplying it by its x-coordinate. That gives us the leverage or moment around the y-axis. We crank through that integral, and we get an answer of 1/3. We do the exact same thing for the moment about the x-axis, m sub x, only this time you can see we're multiplying by the y-coordinate inside the integral. Run that calculation, and we get a result of 2/3. And now for the big finale. We just take our moments and divide by our mass, which was just 1. The x-coordinate is 1/3, and the y-coordinate is 2/3. So the centroid is at 1/3, 2/3. What that means is if you were to cut this exact triangle out of a piece of cardboard, you could balance it perfectly on the tip of a pencil right at that point. Pretty cool, right? That's what these formulas actually do. Okay, that was a great warm-up, but now let's really ramp it up and see how all this works in 3 dimensions. We're going to find the center of mass for a solid hemisphere. Now, thankfully, because a hemisphere is perfectly symmetrical around the z-axis, we already know the balance point has to be somewhere on that axis. So our only real job is to find the z-bar coordinate. Whoa, okay, I know, that looks like a monster, but don't worry, it's just the triple integral for the moment about the xy plane, mxy. We're using spherical coordinates here because, well, it's a sphere. It just makes the math way, way easier in the long run. And the secret to solving these beasts is to just take them one piece at a time from the inside out. So we start with the absolute innermost integral, the one with respect to rho, which is just the radius. All we're doing is integrating rho cubed, which is a basic power rule. The result is r to the 4th over 4. See? 1 down, 2 to go. All right, next we move to the middle integral. This one is with respect to phi, which is the angle coming down from the positive z-axis. We solve this one, and it evaluates to 1/2. See what I mean? When you break it down into little steps, each one is totally manageable.
And the final piece of the puzzle is the outermost integral. This is with respect to theta, the angle that spins around the z-axis. We're just integrating a constant from 0 to 2 pi, which is just 2 pi. And with that, we've solved all 3 parts.
So now all we have to do is multiply the results from our 3 separate integrations together. And when we do that, our final moment, mxy, comes out to be pi times r to the 4th, all divided by 4. Almost there. To get our final coordinate, z bar, we take that moment we just found and divide it by the mass, or in this case, the volume, of a hemisphere, which you might remember is 2/3 pi r cubed. After a bunch of terms cancel out, we're left with this beautifully simple result. The center of mass is located 3/8 of the way up the radius from the flat base. You know, these integration techniques are incredibly versatile. We just use them to find an object's balance point, but they're also totally fundamental for figuring out other really important physical properties, like, say, how hard it is to get an object to start spinning. This resistance to spinning is called the moment of inertia. And take a look at its formula. Hey, that's another triple integral, just like the ones we've been wrangling. The only real difference is what's on the inside. Here, we're multiplying each little piece of mass by the square of its distance from the axis of rotation. That gives way more weight to the mass that's further away from the center. And what's really amazing is that when you go through the process of solving this complex integral for a solid cylinder spinning around its center, all of that complicated calculus boils down to this one wonderfully elegant formula, 1/2 times the mass times the radius squared. It's a perfect example of how calculus can take a problem with infinite complexity and hand us a simple, powerful, and usable result. So, let's end with a question to chew on. You now have the tools to find exactly where an object balances, and you've seen how we can calculate how much it resists being spun. So the next logical step is connecting those two ideas. How does where you push on an object affect how easily it spins? That's where things get really, really interesting, and it opens up a whole new world of physics, but that's a story for another time.